Howdy, folks. I hope you guys had a good weekend. I hope that during the extended weekend you stayed safe and stayed warm. Um, I am going to go ahead and get some stuff going here on the screen. And the first thing that I need to do is confirm we are indeed recording, which is great. That's what I wanted. Um, then, see that I don't need anymore. Okay. Now, what I'm going to do is bring up a couple of things. One thing, or the first thing that I wanted to mention is last Wednesday, I mentioned that we would have um, that we would be using the SSO starting today, Wednesday the 28th. But that is not the case just because on Monday we didn't have class, so I just kind of pushed everything back a little bit in terms of like, oh yeah, you have to use SSO. Um, that will go into effect on Monday. And if you're unfamiliar with that, that just means that you have to log in through your Texas State account. Um, and well, I was going to share this and I'm going to still share this. Um, I posted in, or as an announcement, I posted um, that there would be like there's a link for it, and unfortunately, it did not make it as a hyperlink. So, you know what I'm going to do is I'm going to edit this right here and make that a hyperlink so that that is actually clickable for y'all. In addition to that, I'm going to go ahead and um, throw that into the chat for you so that you don't have to do it right now. Save and don't send. Look at how benevolent I am. That's my SAT vocabulary word of the day. Um, I didn't send you guys an extra email. That's always appreciated, I think, by everyone. But there you go. Hold on to that for next week. You don't have to do it right now. No need to, because everyone's getting credit for participating in today's Zoom. But starting on Monday, if you are not in your authenticated account, you will be unable to join our meeting. Um, so that's the first thing that I wanted to mention. Another thing that I wanted to mention is that you guys have a quiz that is currently up, and that quiz is administered with Proctorio. And along those lines of Proctorio, I have a practice Proctorio quiz, a second practice Proctorio quiz. Um, I've had a couple of people email me, hey, I have this technical issue. And I'm trying to respond to those individually and as best as I can. Um, my troubleshooting is going to be turn the computer off, turn it back on, uninstall this software, reinstall this software, go to the Windows Device Manager, disable this, enable this. Um, Lots of just turn things off, turn things on, and see if that resolves the issue. And it's a very rare instance where someone has something that is beyond those options. Um, this Proctorio practice quiz that is up will be available until Sunday night the 1st, or Sunday the 1st at 11:59 p.m. Um, all I need you to do is participate in it and show that you can take it. If you get the question wrong, that's fine. Chances are, if you get the question wrong, that was intentional, and you're like, "Ha! I'll see if he really means this." And I really do mean it. If you do the quiz, you're going to get that half point, and that's going to go on your final exam. So if you did the first one, you can do the second one as well. Um, so those two are up. You've also got the regular quiz that is due this Friday night at 11:59 p.m. It's 5 questions, 10 points. I've had a couple of folks email me clarifying their accommodations, and I'm glad to make those accommodations, add the time and everything like that. Um, and so if you have not taken the quiz because of that, I will go back. I'm going to be going back through the disability services notifications and making those times or adding those times. If you want to expedite that process, just shoot me an email and say, hey, Dr. Ray, I need time and a half. And I'll go ahead and do that real quick. Okay, so quiz, Proctorio practice quiz. Then a discussion is now up. I went ahead and rather than having the discussions end in the middle of the day on Fridays, I'm gonna have them end at 11:59 p.m. So you have the January 28th discussion that is right here. January 28th. It will close January 30th at 11:59 p.m. It will remain open. And what I mean by that is you will still be able to do it until Sunday at 11:59 p.m. The only thing is that if you don't do it before Friday at 11:59 p.m. and instead you do it, Saturday morning at 7 a.m., there will be a late penalty. If you wait until Sunday to do it, there will be a double late penalty. Um, in the syllabus, I said that if you had basically a 2-day extension or a 48-hour period in which to turn in late work, and it would be a 25% point reduction. Instead, what I'm going to do is 1 day late is 12.5%, 2 days late is 25%. Now, with that said, this is one of the tricky parts about deadlines is that if it's due at 11:59 p.m. on Friday and you turn it in at 12:03 a.m. on Saturday, that is within the first 24 hours late, so that is 12.5% point deduction. Could everyone give me a number in the chat, any number of your choosing, if that makes sense, or a letter if you want me to kind of elaborate on that? Okay, cool. All right. Well, then I don't really have anything kind of organizational to detail. The quiz that's up today, that's only over old stuff. So what we cover today is going to be on the quiz on Monday. That quiz will be opening Monday at 8 a.m. and it will close on Wednesday at 11:59 p.m. Oh, last thing. I'm sharing my web browser. That's what I want to be sharing. I added a link here, AA introduction shorts. That is just a collection of videos, a bunch of YouTube shorts where I go through all the proteinogenic amino acids or the major proteinogenic amino acids and introduce them. So if you're ever like, oh, I need a good resource where I just get kind of a crash course in all the amino acid structures, that's what this is intended to do. Then, and last thing is I've had a couple of people email me and ask, where do I find the old links and where do I find any of the resources from class? This is our homepage recording for the day. That column is everything in there is always going to be Zoom lecture, and that's where the link for the Zoom recording is going to end up. Today's material for the day, there's a PowerPoint file and there's a PDF. I've found and have been told that typically what's more friendly or favorable for the Canvas app is the PDF. And so most people prefer to use the PDF. I have added a link that takes you directly to the PDF. I've added that link to the chat if you want to access that. Daisy, you have your hand up.
I'm sorry. I wanted to know for Wednesday quiz 1, is that the proctorio practice exam, sorry, practice quiz 2, or is that like the actual quiz?
That is the actual quiz.
Got it. Thank you.
And thank you for asking. That's a great question. Anything that you get prompted on, and actually, let me go ahead and if you click that link, it's not going to send you right into it where you have to begin it. It's going to say start quiz and give you that, prime you for that. In the meantime, though, what I'm going to do is I'm going to grab the link for first is the Proctorio practice quiz. There's that. And then I'll leave the quiz just to avoid any sort of confusion. Quiz 1, I'm not going to add that to the chat. I'll send out an announcement reminding everyone of the Proctorio practice quiz. But in the meantime, I'm going to close my email so that I don't get any notifications while I'm in class. And yeah, done. And done. Now, PowerPoint. Okay, so where we were the other day was we were looking into um, kind of physical properties and going through a little bit of a review of some of the things that are really going to be very important for this class. Um, and one of the things that we looked at was amphiphilic molecules. An amphiphilic molecule is a molecule that has a nonpolar region and has a polar region. So it's got nonpolar portion and a polar portion. Now, a great example of that is the building blocks of a lipid bilayer. So a lipid bilayer is going to have kind of an internal chamber, or within the membrane, is it's going to be very hydrophobic. It's a very non-polar region because this right here that I'm putting a red box around is an aliphatic hydrocarbon chain. That aliphatic tail or that hydrocarbon chain, well, it's not going to really like water. And so within this region, you're not going to have a lot of polar molecules or polar substances. Now, with respect to that, one of the things that's important for protein structure and protein folding is different amino acid structures. So what this is right here, this is a protein, or this is a polypeptide. Now, if you're not familiar with a polypeptide, that's the chain that well, a polypeptide is a bunch of amino acids strung together. At some point, those amino acids become a protein when that chain is long enough. Now, what's highlighted here is we've got yellow balls representing polar amino acids, and then black ones representing non-polar amino acids. Now, in an aqueous environment, in an environment, Joel, stop that. In an environment like the, you know, the, sorry, in an environment like a cytosol, what you're going to have is, well, you're going to have a polar solution that this all exists in. And what that means is that these non-polar substances or these non-polar amino acids, they're going to prefer to cluster together. They're going to do everything they can to get away from the polar solution. And so when you talk about a protein or a polypeptide, this large molecule that's, a couple of hundred grams per mole, what that is going to do, or thousands of grams per mole for that matter, what all of these non-polar amino acids are going to do is they're going to cluster together. And that's known as the hydrophobic effect, where these things are driven together. And what ultimately that leads to is a preferred structure like this, where your polar amino acids that I'm circling right here, the yellow balls, are on the surface or on the outside. And that's because they can interact very easily and well with the solution. Okay, so understanding the importance of polarity, I think, is a really important part of this class and understanding how a biological molecule kind of exists and operates. Now, this is something that I don't know if I feel comfortable saying that I find this to be like it's like ionization and how molecules change given different pHs. That's something that I struggled with as an undergraduate. I remember in Gen Chem 2 and then through my biochemistry classes, I was like, I'm just kind of making it through. Um, and I say that, oh, something is in the chat. Sorry, I missed that. Does it work like a barrier? I presume that the does it work like a barrier question that was posed, which I'm sorry I missed that, is in reference to is that in reference to the amino acids, the polar amino acids? Yeah, that looks okay. Uh, Not so much. I guess it could to a degree, but maybe not. I wouldn't say like intentionally. In part because that's putting a like determination or a decision into an inanimate object. Um, but yeah, I guess it does kind of protect those, or it does like yeah, a little bit. It does serve like a barrier. Um, So ionization of amino acids is something that's super important. And, whenever I think about ionization, I always think of phosphoric acid. The reason I think of phosphoric acid is because, well, I don't know why, but H3PO4, it's just this formula that I feel like comes off the tip of my tongue very easily. Now, whenever I draw phosphoric acid, I'm going to draw it like this. Now, this molecule, and this is really helpful for me, and we're going to go into some more examples of this in just a little bit, but this is always really helpful for me because when I look at this molecule, H3PO4, well, it's neutral. It has no charge to it, no net charge to it. Now, this molecule has three ionizable protons. And so what it can do is it can lose one. H3PO4 becomes H2PO4 minus, which that can be deprotonated to become HPO4 2 minus, which that can be subsequently deprotonated to PO4 3 minus. Okay. Now, all of this is taking place based on this molecule's response to its environment. Now, this is super important because amino acids do this same thing. And when amino acids do this, structures like this right here, well, they change based on the environmental conditions. This molecule might have some interactions, and then those interactions might change. So if this is at a pH of 7, a nice neutral pH, well, it's going to look a little bit different if the pH goes up to, let's say, 9. Why is that? Well, that's just because there are some groups that are going to be deprotonated and some groups that are going to be that are going to remain protonated, and those can get closer in proximity to one another to stabilize interactions. Now, this is a if you're like, yeah, I've got that. I understand that. I took Gen Chem 2. Congratulations. And I don't mean that in a snarky way. I just mean that's great because that is something that we'll spend time on and you will have questions on it on exams and quizzes, and then you're going to be ahead of the game. Okay, would H3PO4 be considered a Bronsted-Lowry acid? Yes, it is. Um, Now, in the context of amino acids, I sorry, I should take my watch off because otherwise I'm just going to be irritated by every time I get some nothingness announcement. Um, when we look at this molecule right here on the far left, that's an amino acid known as aspartic acid. And that amino acid has a +1 charge. Now, where does that +1 come from? I'm actually going to erase all this markings. Well, what you're going to do in order to determine the charge is you're going to look at all of the different functional groups. We have a carboxylic acid, carboxylic acid, and then an amino group. Okay. Now, this group is protonated. All three of these groups are protonated, and they're all ionizable. Only one of them has a +1 charge. Okay. So this form of the molecule, the fully protonated form of the molecule, is going to be the most common one at a very low pH. Now, if we jump over here to our far opposite end of the spectrum, this is a molecule that has an overall charge of, let's see, my amino group, no charge, carboxyl, negative, negative. That would be a -2. So what that means is that this molecule is capable of having a charge ranging from +1 all the way to -2. Now, my first question for you guys, and give me a Y or an N in the chat. This on the far left is FP fully protonated. And then on the far right is FD fully deprotonated. Give me a Y or an N in the chat. Can this molecule ever have a -3 charge? I'm seeing lots of N's, and you're spot on. Perfect. Because heck, if you and then opposite end of the question, could this molecule ever have a +2 charge? Nope. So we're living within the confines and the range of this molecule. It can be +1 all the way to -2. And it's going to be every charge between there at some point, all in response to what is the environment telling it to do. Now, understanding this is ultra important. There's a couple of things that are important for understanding this. First of all, the pKa's. This has 3 ionizable groups. It has 3 pKa's. This point right here, pi, that's probably something you haven't heard of before. And what that stands for is the isoelectric point. Or the pi. Now, the isoelectric point is where 100% of the molecule has an overall 0 charge. Okay. So an overall, also you can look at that as a net charge. So a net charge of 0. Now, with that in mind, where the molecule has an overall charge of 0, that doesn't mean that it has groups that are only a charge of 0. Instead, that just means that it's got, well, an equal number or a number of positive groups that are canceled out by a number of negatively charged groups. Now, what we see here on the far left is we see a positive group, neutral, neutral. If we move on to the next form of our molecule, we've got a positively charged group, a negatively charged group, and then a neutral group. So this molecule right here, what's the overall charge of this? Well, positive and negative cancel out. So we're looking at a molecule with a charge of 0. Could you give me an emoji in the chat if that makes sense, or an X if, no, that doesn't make any sense to me. Okay. So we've got kind of a mixed bag of responses there. We have our fully protonated form. And what happens from the fully protonated form to this form, so from form 1 to form 2, is I'd like you to imagine that you have an extremely acidic solution. You have a solution, let's say, with a pH of 1. The hydrogen ion concentration is super high. Anything that can be protonated is protonated. Now, as you add some potassium hydroxide or sodium hydroxide, add a strong base to that solution, what begins to happen? Well, some of those hydronium ions, H3O pluses, they get picked up by hydroxide ions. And so the hydrogen ion concentration goes down, which means the pH goes up. And slowly but surely, what is the purpose or benefit of the isoelectric point? Is it more stable, or is it just a combination we need to look for? That's a fantastic question, and I'll address that right now, and I'll come back to it. The PI, or the isoelectric point, is where, first of all, that's kind of our definition. 100% of the molecule has a 0 overall charge. From a standpoint of, well, what does it do for me? That is where the protein, and I'll say protein/molecule, is least soluble. You could think about that in terms of like experimentally, whenever you precipitate something versus something that stays in solution. Is it a part of the precipitate? Is it a part of the supernatant sort of thing? So if you adjust a solution to a particular molecule's pI, that molecule is going to become a part of the precipitate. It's going to fall out of solution. Could you give me a one if that makes sense, or a letter U if that doesn't make any sense? So now back to this idea of, well, we're deprotonating our molecule. Oh, rats. Okay, we're deprotonating the molecule. And okay, on the far left, we have our fully protonated form. We have all of the groups that can accept a proton have accepted a proton. Our two carboxylic acids both have a proton. Now, these carboxylic acids are going to have different strengths. They're going to have different pKa's. So what that means is that at different pHs, they will lose a proton. Now, our first number that we find is our pKa of 2.10. That pKa corresponds to this first deprotonated carboxylic acid. Now, whenever we adjust the pH of our solution to 2.10, we are going to have a mixture of this molecule, our fully protonated form, and this molecule where we have, well, one group that's been deprotonated. If we adjust our pH to 2.1, we're going to have an equal concentration of the fully protonated form, which I'm going to label with an X, and then our singly deprotonated that I'm going to label with a Y. At a pH of 2.10, 50% of the molecule is going to look like this, and then 50% of the molecule is going to look like this. Now, if we adjust our pH to, let's say, 2.15, slightly more basic than 2.1, which form do you think is going to be more abundant? X or Y? Add it to the chat. Spot on. Y is the correct answer. Now, if we were to adjust the pH to 2.05, then X is going to be more abundant. Now, if we were to put this in terms of like what is the actual percentage X and Y at a pH of 2.15, I'm just going to give you round numbers and I'll say it's 49% is going to look like X, and then 51% is going to look like Y. Those are nice, friendly numbers, rounder numbers. But I want to bring this back to our discussion of PI. Where are we going to be where 100% of our molecule has has a zero overall charge? Now, we've got the numbers shown here, and we've got the formula there, but let's walk through this and think about it from a perspective of, well, how are we going to arrive at that? When we deprotonate this first group, this first carboxylic acid, we're going to completely deprotonate that before we move on to the next one. I always think of titration curves like this as being very organized and orderly. This says, hey, you know what? We're going to completely take care of one group before we move on to the next. It's the opposite of me with any sort of tasks. Like, oh, yeah, I need to clean my car and do my laundry. What should I do first? How about both of them? Well, that's not an option. You cannot do two things literally at the same time. And so then neither of them really get finished. But the point here is when we look at molecule Y, we have this first group that gets deprotonated. Whenever that one is completely deprotonated, we're going to move on to this next carboxylic acid. This other carboxylic acid has a pKa of 3.86. Okay. Now, what this means is if we are continuing to increase our pH from 2.15, let's say that we get up to 3.0. Oh, not maybe not 3.0, but let's say that we get up to 2.3. Well, we're going to have X and we're going to have Y. And we're slowly but surely going to be increasing the amount of y. Does everyone agree with that? Give me a J in the chat if you agree and follow that. As we continue to increase our pH, we're favoring y more and more. And when we favor y, that means we're kind of getting rid of x. At some point, we will continue increasing the pH, making the environment more and more basic until we have no x remaining. And everything looks like y. Now, I'm going to get my phone so I can use my calculator. And at that particular point, we've got 2.10 plus 3.86 is 5.96. Divide that by 2, and that's going to be 2.98. Now, a fair question there is, why did we divide it by 2? The reason that we divided it by 2 is because at 2.10, this point right here, we have a 50-50 mixture of X and Y. Could you give me a 3 in the chat if you follow that and you're good with that? Okay. So at 2.10, we've got a mixture of those two. Now I'm going to label these other structures, Z and A. Okay. When we get to a point where, or sorry, the next place that we're going to go, just in terms of pKa's, is 3.86. When our pKa is equal to our pH, when our pH equals 3.86, we've got 50% of our molecule that looks like Y, and then 50% of it that looks like Z. Could you give me a 6, 7 in the chat if you agree with that? Okay. Great. Now, what will exist when our pH equals 9.82? Which forms of our molecule will exist at that point? Z and A. Perfect. Now tell me, when your pH is 9.82, what percentage of the molecule looks like X? Pretty much 0. What about Y? Again, pretty much 0. Chances are that it looks a little bit like Y more so than it looks like X, but X and Y, for all intents and purposes, when our pH is 9.82, it's basically not there. So the way that I want you to think about this is, and the way that I think is helpful to think about this is, I'm going to put myself in a little car, a roller coaster. And what I'm doing is I am in the solution and I am traveling along this titration curve. And at different points, I pause and I take a look around. And at my first point, my pKa 3.8 or 2.10, I look around and I've got 50% that looks like X, 50% that looks like Y. Ooh, fantastic. I continue on. At any point to the right of this, well, what's happening to X? The market share, I don't know, there's my business speak for the day. The share that looks like X is going down. The share that looks like Y is going up. It's going to continue to go up until right here, where 100% of my molecule looks like Y. Now, as soon as I go above my PI, which is 2.98, as soon as I go above 2.98, now all of a sudden, what happens to Y? The amount that looks like Y goes down. So what does that mean for Z? Z goes up. So if I were to pause like right here or something, I might be looking at, well, 98% is Y and 2% is Z. As I continue in my awesome little roller coaster along this, I'm going to reach that second pKa, pKa2, 50-50, 50% Y, 50% Z. Now, this is a little bit of an aside, but it's the same in principle to calculating PI. Could anyone tell me if your PI says that's where 100% of your molecule has a zero overall charge? Could anyone do the calculation to tell me where does 100% of your molecule have a -1 overall charge? So where, and I'm looking for a number. I'm looking for a pH. At what pH will 100% of my molecule have a -1 charge? So, okay, I think I'm seeing it. Seeing 6.84 as a popular answer. You're right. It's 6.84. Okay. Now, I say it's the same because the way you do the calculation is the same. What you're going to do is, and the way that I always like to think about these molecules is I like to say, all right, well, what are my charges for my molecules? If you remember, we started out, our range is +1, 0, -1. This one, this fully deprotonated, is -2. So that's how we started. We looked at our molecule and we said it can range from +1 to -2. Now, this point right here, that was where 100, that was our pKa of 2.10. Our next pKa is 3.86. Then our next is 9.82. All right. What we did to solve for our PI, where 100% of our molecule had a zero charge, was we said 2.10 plus 3.86 divided by 2 gives us 2.98. Could you give me an emoji in the chat if you're good with that calculation? Okay, great. Now, we're going to do the same thing if I'm looking for, well, what if it's -1? So I'm going to take this number, add those up, divide by 2. That's my PI. 3.86, 9.82. I'm trying to find out where 100% of it has a -1 charge. Add those two up, divide by 2. And that's how I get 6.84. Okay, now I bring this up because I want you to think about PI calculation as, well, you're just using pKa values. You're adding them up and dividing by 2. You're trying to find a specific point between these two pKa values. Now, what makes the PI unique is that is where 100% of your molecule has an overall zero charge. Now, with respect to the PI, there's another term that I want you to be familiar with. The Zwitter ion form. If you look at these molecules, they range from this first one having a plus charge and neutral groups. This next one, where we've got plus charges and minus charges. Your Zwitter ion form is where you have positive and negative charges on the molecule simultaneously. Now, with that said, there's a little bit of, if you think about like a Venn diagram, there's some overlap between the Zwitter ion form and the PI, where the molecule has an overall zero charge. So there is some overlap there, but what I want you to know about a Zwitter ion form is where the molecule has simultaneously a positive and negative charge, or positive and negative charges. So think about calculating your pi as being like underneath the Zwitter ion thought and consideration. Okay. So this right here, looking at a titration curve, analyzing a titration curve is something that I know you've done before, and maybe it's been a minute. I know that this is something that folks struggle with. And I don't want to say that to be like, and therefore you will struggle with it too. Instead, I want you to think like, you know, for lack of better instruction, be honest with yourself and say, yeah, I understand the curve. I can do that. But what that represents is something I kind of struggle with. So when we look at our amino acid structures, one of the things that we're going to do is we're just going to point out, okay, what are the ionizable groups? And how do those groups change? Because I think that will help us do a couple of things right from the beginning. And that is to think about the first thing that we did here. We looked at this molecule and we said, what are the extremes? What is the most positive that this molecule can be? And what is the most negative that this molecule can be? And in order to do that, you have to be able to look at those different ionizable groups and say, that can be positive, that can be negative. That is positive or neutral, that is negative or neutral. Okay. Now, another way of looking at that is, well, I always think about the number of pKa groups that something has, and or sorry, pKa values, and I'll say, okay, well, each pKa value corresponds to a horizontal region of a titration curve. So this is relatively horizontal. This is 2, this is 2. If a molecule has 3 pKa values, you're going to have a titration curve that has, well, 3 horizontal regions. Now tell me, if I were to show you this titration curve, how many pKa values do you think that the molecule that corresponds to this, how many pKa values does that have? 2. Absolutely. Okay. Can you repeat again how or in what way the Zwitter ion is applied to the curve? Think about the Zwitter ion as being reflective of when a molecule can have positive and negative charges simultaneously. In terms of, well, am I going to give you a titration curve and ask you to circle the Zwitter ionic region? Unlikely. But when you look at this, I would say, well, this group has positive and negative, or this form of the molecule, Z and Y, both have positive and negative regions. So those are both Zwitter ion forms of this amino acid. Where would you find that? Well, you'd find that anywhere above pKa of 1 and below pKa of 3 as the predominant forms. Now, we're going to get more into that when we talk about specific amino acids and look at their Zwitter ion forms. But I want you to be able to, does a Zwitter ion need to be neutral? No, I do not believe that it does. Because it has some of those groups. It might be positive, might have one positive, might have 2 negatives. So yeah. Now, I want you to be able to look at a titration curve and quickly assess those sorts of things. In addition to that, I want you to be able to look at a molecule like this right here and say, okay, well, I'm looking at it, it's fully protonated, +1. I'm looking at this, okay, that's -2. I don't want you to like struggle over it and be like, oh, but is this a trick? The way that the molecule is drawn and shown, it's not a trick. It's good for you to look at it and be like, yeah, but this is all in equilibrium. You're right, it is. But there is not going to be a form of this amino acid that has a +2 charge. It simply can't exist. And that, or without some sort of major modification. So I think that one good habit to have is to, whenever you see a molecule, to think about, okay, well, and the way that I always like to do it is I like to think, okay, what if this molecule, or let me rephrase that. This molecule is fully protonated. What is its charge? Okay, +1. This molecule is fully deprotonated, -2. How do we get there? Well, we've got to deprotonate one group. And whenever we do that, we go from a +1 charge to a 0. When we go from a 0, deprotonate that, it's going to be -1. And then deprotonating again, it's going to get to -2. We've got 3 pKa's. We've got 1, 2, 3 horizontal regions. If we were to make an approximation, where is this +1 form the most abundant? It's going to be right about here, to the left of our first pKa. Because as soon as we hit pKa 1, or as soon as we hit pH equals pKa 1, then at most, this form right here is 50%. And this one is 50%. Okay, so in the event that you're not struggling necessarily, but you're like, wow, that's all of this was familiar, but it still seems sort of tough to grapple with. Don't worry, we're going to come back to that. And we're going to look at lots of examples of these in the context of different amino acids. Now, with that, day two, we're now going to pivot to a discussion of nucleotides and nucleic acids. Now, this is something that I know for some folks, there's going to be a little bit of review here. Um, but if this isn't review, awesome. And I will do my best to make sure that you kind of walk away with the important parts about this. So we will be talking about nucleotides and nucleic acids. Nucleotides and nucleic acids. And what's the big idea? What's the big deal? DNA is deoxyribonucleic acid, RNA is ribonucleic acid. Now, there's a couple of very important experiments in the history of cell biology, molecular biology. The first one is the Hershey-Chase experiment. This was conducted in 1952. And what this did was it more or less solidified the idea that DNA carries genetic information. So, what was done with this was bacteriophage were studied, and they were raised in different environments. So, in one, they had radio labeled sulfur, and then another one had radio labeled phosphorus. Now, these two things were selected because sulfur is uniquely found in proteins. So, sulfur only in proteins. Phosphorus only in DNA. And what happened was they incubated these bacteriophage with some E. coli and then basically took a look at them and said, all right, well, we're going to do some centrifugation to separate the radio labels from the non-radio labels. And if the bacteria, if the E. coli have the radio labeled sulfur, that would mean that the bacteriophage transferred that radio labeled sulfur into the E. coli. Now, they did this separation where they separated the bacterial cells from the bacteriophage, and they said, lo and behold, the bacterial cells do not carry that radio labeled sulfur. Okay, so we separated them based on their densities. And whenever they saw that, well, the E. coli doesn't have the sulfur, then essentially what that means is, yeah, the bacteriophage was able to infect it, but it did not infect it with anything that carried sulfur. Now, the next thing that was done was they also took a look at, well, with this phosphorus, they let the bacteriophage infect the bacteria. They separated by centrifugation. the bacteriophage from the E. coli, and then they looked for that radio-labeled phosphorus, and they found that that radio-labeled phosphorus was indeed in the E. coli. And so that was an indication that, hey, the radio-labeled phosphorus was transferred from the bacteriophage into the E. coli. So these this transference of or transfer of the radiolabeled phosphorus is our indication that, well, we did indeed transfer the genetic information. And so the Hershey Chase experiment was of fundamental importance for that, where it kind of confirmed, or maybe not confirmed, but it arrived at the conclusion that DNA carries genetic information. Now, a couple of years later, um, Francis Crick, Jim Watson, and Maurice Wilkins were given the Nobel Prize in chemistry, I believe. I always get it mixed up. Was it chemistry or medicine and physiology? But they kind of elucidated the double helical structure of DNA. And they did it with the help of Rosalind Franklin. She was deceased whenever it was awarded. I don't think that it would have been awarded to her anyway because of many different factors. Um, but these rascals right here were like, hey, let's stand on the shoulders of a giant and draw a conclusion. And they did. And so they were awarded the Nobel Prize for that. Oh, how about that? Medicine says it right there. Whoops, Joel. So our double helical structure, there were other theories like Linus Pauling had a theory at the time of a triple helical structure, but ultimately that went kind of by the wayside and didn't really stand up to much more experimentation. Now, next up, the Human Genome Project. This guy right here is a fellow by the name of J. Craig Ventnor. He was a part of this. The Human Genome Project was a joint venture, a private public venture that was, well, there was publicly funded and privately funded portions of it that they worked together and they arrived at a, a model of the human genome. And that was in about 2003. There was a publication in Science, a publication in Nature about it. This is something that people continue to analyze and continue to work on because there's regions of the human genome that it's very difficult to actually get a valid and verifiable sequence on it. So this is something that there's still updates to it being done pretty regularly. The one thing that I left out of here was a major, I don't know if I don't know if I want to call it a discovery, but a major part of biological research, and that was the PCR, the polymerase chain reaction. And that was a fellow by the name of Cary Mullis. He's a character. He's deceased now, but I think he credited himself but he also credited I think it was like a neon green raccoon that he saw when he was hallucinating. And that helped him come up with this theory. Okay, so with that said, these are just some major points that I want you guys to be familiar with throughout the history of DNA and DNA analysis. Now let's talk about the components of DNA. There's a sugar, and ribonucleotides, the pentose sugar is ribose. So pentose, a 5-carbon sugar, that sugar specifically is ribose. In deoxyribonucleotides, the pentose sugar is deoxyribose. Now, which one of these do you think has one fewer oxygen than the other? R for ribose or D for deoxyribose? Booyah! Great job, everyone. Spot on. Now, here are our two structures. Here are our two sugars. Our ribonucleotides have this structure shown on the left, deoxyribonucleotides on the right. One of the things that I want to draw your attention to is the numbering. I've circled 1 prime, and that is carbon number 1 on this sugar. This 1 prime, or that prime designation, is to distinguish it from any of the atom numbers of the nitrogenous base right here, which here we've just got base as kind of a filler. 1 prime, 2 prime, 3 prime, 4 prime, and 5 prime. We have a 5 carbon sugar known as ribose. It is a cyclic ring molecule. The difference between a ribonucleotide and a deoxyribonucleotide is the presence of this hydroxide group or this OH on carbon 2 prime. Now, on carbon 5 prime is where you're going to find a phosphate. Now, a nucleotide, that is a different thing from a nucleoside. Nucleotides are composed of a nitrogenous base, yeah, a sugar, ribose, and at least one phosphate group. Okay. So can you tell me, is this molecule here, is this a R ribonucleotide or a D deoxyribonucleotide? Spoiler, there is a way to tell. For everyone who said R ribonucleotide, you're absolutely right. Chances are that you looked at carbon 2 prime and you saw this OH and said, aha, there's an OH there. Therefore, this must be a ribose. And if you jump back, well, here is our deoxyribonucleotide. Look at that carbon 2 prime, and that's going to be your way to tell, are we talking about a DNA deoxyribonucleotide, or are we talking about an RNA molecule? Now, this phosphate group right here, this is so a nucleotide consists of three things: a nitrogenous base, a sugar, and at least one phosphate group. A nucleoside consists of only a sugar and a base. So if I did not have this, I would be talking about a nucleoside. Now, nucleotides, I think many of these you're probably familiar with if you've taken a biology class. If you haven't, you maybe got some familiarity with them through pop culture or something like that. Your discussion this week asks you about the first time that you ever were exposed to DNA or became familiar with it. And I mentioned my own personal experience, and that was June 11th, 1993. My family went to Shulman 6 movie theater in Bryan, Texas to watch Jurassic Park. And the first time they said, Dotto DNA, I was hooked. I love that movie. It's the best movie ever made. Nowhere to argue with that. That is a fact. Certifiable, verifiable. But that was the first time I ever heard about DNA. And ever since then, I've seen it in any number of movies, any number of other books or anything non-science. And that's kind of what I'm looking for in that. But if you're like, well, it was whenever I was reading the dictionary when I was 4 years old. Okay, great. Now, what I want to draw your attention to is here, Tropic Thunder, way better. Tropic Thunder's funny, yes, but it's not an experience like Jurassic Park, but we'll proceed. So here what we have is a nucleo, and this term is this might be a little bit confusing, but we've got a base, we've got a sugar, and then we have at least one phosphate group here. Many people will refer to this as a nucleoside. Nucleoside. So that's in reference to a base and a sugar. Nucleoside triphosphate, where you have 1, 2, 3 phosphate groups. Now, these phosphate groups are labeled or are identified as alpha, beta, and gamma based on where they are on your 5' carbon. So this 5' carbon, this is an alpha phosphate group, a beta, and a gamma phosphate group. There are nucleotide monophosphates, diphosphates, and triphosphates. If I had $1 for every time I heard nucleoside triphosphate or nucleotide triphosphate, I'd have plenty of dollars. People have a tendency to mix those two things up quite often. Now, the bases are what distinguish these things from one another, in addition to this 2' carbon. Now, again, if we look at this molecule that's shown right here, is this a DNA molecule or an RNA molecule? Well, by the presence of this 2' OH group, it is an RNA molecule because we've got that 2' OH. Now, the nitrogenous bases differ from one another. There's adenine, guanine, cytosine, uracil for RNA, and then adenine, guanine, cytosine, thymine for DNA. Now, one thing that is it's worth your while to put is this lowercase d in front of the three-letter code that corresponds to the actual nucleotide. That lowercase d indicates you're talking about a deoxy. So the presence of that lowercase d indicates that, well, it's a DNA molecule, so no OH at C2 prime. A corresponds to a nitrogenous base known as adenine. M corresponds to the number of phosphates, mono, and P corresponds to phosphate. ADP, well, that's adenine diphosphate. DATP corresponds to deoxyadenine triphosphate. Now, we haven't looked at these nitrogenous bases, but I see a question. For the sugar, are the carbons always numbered right to left? That is a fantastic question. And it's not so much right to left as it is, well, where is the nitrogenous base? The nitrogenous base is going to end up on your C1 prime or carbon number 1 prime. I'm thankful that you asked that question because that's a great question. Now, what we're going to do now is look at the different nitrogenous bases. So, there are several different nitrogenous bases. There's two major classes, your purines and your pyrimidines. Purines are bicyclic. They have two rings. A purine has two rings, whereas a pyrimidine is a single ring, monocyclic. Now, your pyrimidines are cytosine, thymine, and uracil, whereas your purines are adenine and guanine. Now, the numbering conventions for these, your pyrimidines start at I always just think about it as the 6 o'clock position, and it goes clockwise. So 1, 1, 1. That nitrogen is your highest priority group. We're going clockwise, 2, 3, 4, 5, and 6. 2, 3, 4, 5, and 6, and so on for the uracil. Now, one thing that's worth noting is this nitrogen is the atom that connects to carbon 1 prime. So if you think about the connection between a pyrimidine and a ribose, or heck, deoxyribose, you're talking about an atom number 1 connecting to 1 prime. So you immediately have some necessity and need for that 1 prime designation, because otherwise it's, well, atom number 1 connects to atom number 1. So that's why we use that 1 prime designation for the sugar itself. Now, if you look at your purines, in the cases of both your purines, your numbering starts at this nitrogen that's kind of in like your 10 o'clock, 11 o'clock position if you're looking at it on a face, as the face of a clock. And that is going to be counterclockwise. 1, 2, 3, 4, 5, 6, and then 7, 8, 9. This nitrogen right here and that nitrogen right there is the one that connects to C1 prime. C1 prime. So a purine plus a ribose connects through atom number 9 to 1 prime. So that's where those are some of the points there. Now, what do I want you guys to be able to do? Is I want you to be able to identify all your nitrogenous bases. If I show you the structure as like a question on an exam, I want you to be able to pick that one out. Um, this is just sort of my suggestion. When it comes to this sort of information, I always like to triage it. I always like to start broad and say, okay, I'm trying to learn my nitrogenous bases. Okay, cool. What's the first step? Well, I want to divide that. Yeah, there's five nitrogenous bases. I'm going to divide into two major groups, your purines and your pyrimidines. What does a purine look like? Well, that's got the two rings. What about a pyrimidine? That's got one ring. Okay, now there's two purines and there's three pyrimidines. What make them different from one another? If you look at carbon number 2 in your purines, you immediately see the stark difference. Carbon number 2 is just a CH where in adenine, whereas in guanine, it has that amine group outside of it. I think that's just sort of a helpful thing to just sort of remind yourself as this is a way I can discriminate between these two molecules. That NH2 on carbon number 2 gives me my way of distinguishing between my two purines. Now, my pyrimidines. Okay, well, I've got my numbering. And if I look at carbon number 2, those are effectively the same in cytosine, thymine, and uracil. Okay, but what about where do I see a distinction? Oh, well, carbon number 4 of cytosine, that has an NH2 on it. Okay, now let's see, that's a little different. But then if I go to carbon number 5, that's got a methyl group on it. Oh, and only carbon number 5 of thymine has that methyl group. So when I'm thinking about this, I'm going to say, all right, my pyrimidines, I'm going to look to C4 and C5. And I'm going to say, okay, if C4 has NH2, that's cytosine. If C5 has a methyl, that is thymine. If it doesn't, if C4 and C5 don't tell me anything about presence of those, well, then I'm looking at uracil. So that's kind of how I process this information, the way that I think that it's helpful, because then is our cytosine missing an H on number 3? Cytosine. No, it's not, because this right here, this nitrogen, remember, nitrogen really likes to have 3 bonds and a lone pair of electrons. So it's got a lone pair of electrons right there. And that's, yeah, that will be helpful. We can come back to this after a little while. That's helpful for looking at some other things. Okay, so now when we look at nomenclature, the prime numbers are super important because they relate to the sugars. Now, non-prime numbers refer to atoms on the bases. The phosphate group may be attached to the sugar at either of two positions. It could be attached at C3 prime if it is what's known as a 3 prime nucleotide, or on 5 prime if it's a 5 prime nucleotide. Now, with respect to this, oh, and actually, let me jump back for a second, just so I can show you. Well, this right here would be our 3 prime. So your phosphate's either going to be here, or it's going to be there. Let's scribble that out. Okay. Now, done. There are names that are maybe most unique and precise. Adenylate, for instance, or guanylate, uridylate, and cytidylate. The ones that I want you to be most comfortable with and familiar with is this term right here, adenosine 5' monophosphate, guanosine 5' monophosphate, because that tells you kind of enough information. That tells you are dealing with the nitrogenous base, guanine, the sorry, the sugar, sorry, that tells you the nitrogenous base that you're talking about. It tells you the sugar by leaving off deoxy, because deoxyguanosine 5' monophosphate is different from guanosine 5' monophosphate. Our symbols for these are the single letter code G, the 3-letter code GMP. The nucleoside, so A nucleoside is nitrogenous base plus your sugar. Well, guanosine, uridine, deoxyguanosine, deoxythymidine, deoxycytidine. Um, I want you to be able to distinguish between what is a nucleoside versus a nucleotide, and does this molecule, like, what is that? Does this molecule have a phosphate? Yes or no? If we're talking about a nucleotide, you're going to define where it is. So if you ever saw adenosine and you were asked, is this a nucleotide or a nucleoside? If you only see adenosine, the answer is nucleoside. Does everyone follow me on that? Give me a 5 in the chat if you follow that. Or anything else if that doesn't make sense. Okay. So can you repeat one more time? I absolutely can. So adenosine, if you saw that, actually, deoxy. Deoxyadenosine. If I wrote deoxyadenosine, just that word, and I asked you the question, is this a nucleoside or a nucleotide? Well, by it not mentioning a phosphate, the correct answer would be a nucleoside. So if you saw instead deoxyadenosine, adenosine, 3' monophosphate, and I said, oh, this right here, is this a nucleotide or a nucleoside? Well, that does require a couple of steps. Then you'd say, oh, well, it says monophosphate, so there's at least one phosphate. Well, that checks the box for a nucleotide. Does that make sense? Okay, cool. Now, next up is abbreviations. Single letter A, G, C, U, T. Nucleotide, AMP, ADP, ATP. For the most, what just happened? Just happened. Okay, that was weird. Now I don't know what parts of my computer are working. Okay, I have multiple monitors, and I'm not trying to flex on you guys there, but I lost something. Okay, but here I am in the back. Your nucleotides, deoxynucleotides are going to see DEOX. Why? To demonstrate that. Now, next up, your various monophosphates. Well, you've got adenosine monophosphate, 5' monophosphate. Adenosine 3' monophosphate. Adenosine, what on earth? Adenosine 2', 3' cyclic monophosphate. Just get out of town. That's bananas. Well, if you've ever heard of CAMP, cyclic adenosine monophosphate, that's what's known as a secondary messenger. That's a molecule that's produced to send a signal downstream or at a different location. Cyclic AMP, that's what this looks like. This is an example of what that looks like. Cyclic AMP could also be 3', 5' cyclic adenosine monophosphate, in which case the phosphate's over here. Okay. Then there's lots of, so nucleotides don't simply exist as a part of genetic information. There are lots of different cofactors that have ADP. Or my computer's being weird. And yep, there we go. Unnecessary. Oh man. Okay. Well, stop share temporarily. Start share. Computer. Okay. I'll move this out of there. Move that out of there. Okay, there we go. There are things that have a come on. Swap. Yeah, there we go. Yeah, there we go. Fixed it. Joel, you're a genius. Okay. So you're going to find nucleotides and nitrogenous bases in a number of different examples and other different scenarios. Um, For example, if you've ever heard of NAD or NADH, that is an electron carrier that's involved in the electron transport chain. That is, how your cells get a lot of energy by using this NAD and producing NADH. Carries a, yeah, it's an electron carrier and they can carry out a lot of oxidation reduction reactions. Similarly, there's flavin adenine dinucleotide or FAD that also contributes to electron transport chain. Then, last but not least, and this is where we're going to go out on top, is coenzyme A. This is a molecule that is central to going from um, glycolysis, your sugar breakdown, into the citric acid cycle, among many other things. But this coenzyme A has a component to it that is a nucleotide. So, as much as we think about nucleotides and DNA as being critical to DNA, sorry, carrying genetic information, that's not their only role. They do contribute to other things and other processes. Okay, I'm going to go ahead and stop my share. It is 4:46. I want to say thank you guys very much for coming to class. Um, I'm going to stop my recording. If anyone has any questions, they're more than welcome to hang around for a little bit. I apologize for the technical issues that just happened. Still looking around my computer to see what that was. Um, Other than that, though, have a great weekend and email me if you got any questions. The quiz is not open note. There's a